Okay, good morning everybody. I hope everyone's having a wonderful day. So I'm going to pick up from where I was last day. So last day I started talking about open addressing. In particular, I started talking about linear probing. So the idea in open addressing is that we're going to use all of the slots in our table. And the thing is, we're just going to store our records directly in the table. So as opposed to separate chaining where we just simply use more memory. And one drawback of the separate chaining approach is that we might use too much memory. So the idea is that we're going to try to put all of our records in the table itself. You can just think of it literally like a lookup table if you'd like. So that brings me to a couple of things I wanted to bring up that are drawbacks of this approach and a couple of issues, and I'm hoping that we'll be able to remedy some of these issues. So I'm hoping we can think of a little bit about this today. So the first thing is I talked about the remove operation for when we're doing linear probing. One issue that we had was when we think about me, say think of me as the bunny rabbit, when I perform my hops to find the successive spot that I could fit in, for example, for a put operation, or for example, I'm performing my hops, I'm going from one spot to the next, each time I do this, I will follow some sequence of hops. And the idea was that we put these so-called delete markers, these delete labels. You can think of it as just some unique value, for example, that's different from the keys, and it's not null. And we put this down there to ensure I can successfully, with my bunny, which is analogous to me examining these locations in the probing sequence, I want to ensure I can continue hopping along. I don't fall into a hole where a null would be. So the idea is that I put these deletes in here. Now, one way I could get rid of these deletes is by modifying the algorithm we have for put. Now, I didn't go through the pseudocode for put. It's in the notes. I encourage you to take a look at it. But the idea we talked about, we've definitely seen plenty of examples of using it. So the idea is really quite simple. Remember, we just follow the probing sequence. We find the next available spot where we can insert it. That would be where a null is. But here's the thing. I can always reuse these ones that say delete in them, but there's a catch with this, and this is something our algorithm actually doesn't do, is it actually doesn't check for duplicates first before it does the insertion. Instead, it does all of the hops to find the spot that's available for the insertion. This guarantees, by the way, that you're going to check for these duplicates. But the thing is, if I preemptively insert into a delete spot as opposed to keep examining the rest of the slots that I could successfully go across, if this happens, I may miss a duplicate. So if you wanted to modify the put algorithm we have to reuse the delete slots, you can always check for the duplicates first. So first, just go through the probing sequence as you would for the insertion. And then if you don't run into a duplicate, then go through the probing sequence again or keep track of where you found that first delete. In fact, probably the latter is probably the more efficient approach here. So that's one way you could get rid of these deletes, is you could reuse the space. So think it a little bit environmentally here, reusing my space here. The other thing is that the table, of course, can fill up with deletes if I'm not doing a whole lot of insertions, right? Well, if that happens, one big problem we're going to have is that you're going to start wasting space in the table, because remember, these deletes don't represent records anymore. They're supposed to be deleted. So you can think of them like we're marking them for deletion. But the thing is, if they're just sitting around in there and they start filling up the table, it's going to degrade the performance of our hash operations. So for example, our get, put, and remove, they're all going to start taking longer because the chances we're going to run into what we're going to talk about in a moment will increase, because now I'm going to have all these deletes that I'm going to hop over by default. So imagine my bunny rabbit is just going to have more hops to make because they're all just going to have to go over all of these deletes. So one way you can resolve this issue is you can imagine you take a look at what's going on with your hash table. If you have a lot of deletes in there, does anybody have any ideas of how I could get rid of all of those deletes? And keep in mind, I'm not looking for the most efficient way to do this, but does anybody have any ideas of how we can resolve getting rid of all of these deletes? It doesn't have to be the most efficient way. So think of a way, remember that the hash table, especially when we're using this open addressing, yes, exactly, rehash. So what you do is you take every one of your records in the table, you're going to rehash them back into Either you're going to just rewrite this entire table by just making a copy of it, you're going to rehash into this new table, then you're going to reassign it to the new table. So you could do this, you can always make the table bigger, but obviously the big idea here is you just want to ignore all of these delete tags when you're building up the new array. And that's how you could get rid of all the deletes. So you can almost look at it like a maintenance step. And it's actually how very often lazy deletion gets used, is that all of these markers periodically will get wiped out so that you can put something else there. So that's one issue that we can always resolve. So one way you can get rid of this is that you could always, every once in a blue moon, you could always rehash periodically if you find yourself really not liking these things here. But remember, that's one thing to just take and keep in mind. The other issue is what I alluded to last day. In fact, we've seen it in one of our examples, is this issue that it forms this thing we're going to call a cluster. So suppose I give you this example here. Say if I have a table with 7 slots in it, and say my hash function is k mod 7. I'm going to put in 1, 8, 3, and 29. So if I do this, I'll say if I use h of 1 is just 1, right? So it's going to go right here. I'm just going to ignore the fact that there might be a data attribute here. I'm just going to look at the keys just for the sake of time for us. So next, I'm going to go through 8. Okay, well, what should h of 8 be? What's h of 8, everybody? What's h of 8? It's just 1, right? But as we established last day, if we get a collision, so we're right here, we're going to have a collision. So I'm going to then apply the probing sequence. So the first thing I do in the probing sequence is I examine this spot. That one's not available, so I'm going to add 1 to that. And I go to the next one. And now I can put it right here. So notice I hop on over this way. So I'm the bunny rabbit, I'm hopping. So next, let's try doing 3. So h of 3. So let's try h of 3. Okay, well, 3 is much easier, right? It's less than 7. I was about to write 1 down, but no, it's actually just 3. So that's just 3, right? So we're just going to put that right here. And now let's do 29. H of 29. Can somebody tell me what h of 29 is? Yeah, h of 29 is 1. Very good. Very good. But that's a problem, right? Well, look at this. Okay, so I'm going to try putting it here. Well, that's not available, so I'm going to perform a hop. Think of my bunny rabbit. I'm going to hop to the next available slot. Okay, well, that's not available. That's not available. But this one's available, so I can put 29 right here. So this is actually what we would call a cluster. So in linear probing, the way it takes this form is because every time I perform one of these insertions, for example, what happens is there's a possibility I'm going to have to apply the probing sequence, right? But the thing is, our probing sequence increments steps by 1, right? So when I do this, it goes to the next slot available, right? So every time, say if I put in another record, say if it's another one, say like 9 or something, well, it'll end up somewhere in this cluster and it'll have to hop all the way down past the cluster, right? It'll only grow the cluster by 1. Does everybody see that? Well, the existence of these clusters degrades performance as well. In fact, if you could almost think of, when we talked about the worst case analysis for linear probing, it was just like we had one giant cluster. So this is another issue, is that in linear probing, we get these clusters, and the thing that makes these specifically an issue with linear probing is that all the elements are adjacent to each other like this. So just to give you kind of an idea with this, is that, okay, so how do we deal with this? Well, think of our little bunny rabbit. I don't know, think of my cute little bunny rabbit. Here's my cute little bunny rabbit. Here's my cute little bunny rabbit. Here's my cute bunny rabbit. Okay, there's my cute bunny rabbit. A bunny rabbit does little hops, does 1 each time, right? It increments by 1. That's what we did for linear probing. So we always do 1 hop, right? We hop by 1. So here's what I'm going to propose to try to resolve this issue with the clusters. Now, this doesn't entirely destroy the concept of clusters, but it most certainly will eliminate this issue in the exact way we had it with linear probing. So the idea is we would like to mitigate these clusters. So here's an idea I'm going to propose to you. Instead of us having just a bunny rabbit like this that just has one hop, what I'm going to do is I'm going to give my bunny rabbit, I'm going to like take this bunny rabbit, I'm just going to like give it some rocket boots. So it's going to have rocket boots. So the bunny's going to have rocket boots, and instead of having it where it does one hop, we're going to try to make it so it makes larger hops. So one way we can try to resolve two so we can make larger hops, right? So there's a couple of different ways you can achieve this. Now keep in mind that still, you can argue that, okay, if I make them all of equal length, that still is a problem, right? If I hop them all by 3, it's just the thing is I'm offsetting the hops now by 3 as opposed to just being 1, right? So there's a lot of ways we can modify these rocket boots. So for example, we talked about linear probing. There's also a concept called quadratic probing, where the probing sequence will increase by, say if we have it where it's just +1, the next one would be, the next square number would be +2. Sorry, it would be +4, because 2 squared is 4. Then we have 9. So like you would increase it by going up by quadratics, like at each square number. So that's one way of doing it. I'm going to show you a little bit more of a general way of doing this that takes it a step further. So instead of it being where now the hop is relative to some size of a hop in terms of some fixed number sequence, instead it will be that it depends actually on the key. So this will actually cause it to mix up the hop sizes. So instead of it just being, oh, I go 1, then I go 2, 3, 4, 5, or 1, 2, 1, 4, 9, 16, etc., etc. I'm going to make it so it actually depends on the key. So we're going to give our rocket-powered boots the ability to do this. And that will hopefully mitigate this issue with the clusters. So does everybody understand the strategy we're going to use? So instead of it being where this hop size is going to be just a 1 or a 2, I'm going to give this the ability to hop based on some other hash function based on k, the key. So I'm going to introduce a second hash function that's going to be used to determine the hop size. So that's going to be how we're going to resolve this issue. So I'm going to give our rocket power boots, so instead of it just being one hop like this, I'm going to give the ability for the bunny to do big hops, big hops. So it can hop all the way around this table a lot more. So it will prevent us from having these clusters. Now, this is just a way of preventing this clustering from happening. So let's talk about it, and this actually is the idea of double hashing. So what I'm going to do is I'm going to define something we're going to call the secondary hash function. So you know when I talked about these hops being another hash function that's going to depend on k? So the k is the input for this hash function. We're going to call that the secondary hash function. This is in contrast to the one that we use the hash into the table preliminary. That is our primary hash function. So this is just some jargon for discussing hashing in this context. So the primary one is h. The secondary hash function, we'll call it h prime. So we're going to let h prime of k, so k is going to be the input for this function, will be a secondary hash function. So incrementing by, instead of incrementing by 1, we're going to increment by multiples of h prime of k. So we're going to go up by hop sizes of h prime of k. So it'll be 1 hop, that will be the result of h prime of k, then 2 times that, then 3 times that, then 4 times that, and that'll be our new probing sequence. So instead of it being 1, 2, 3, 4, 5, 6, etc., etc., and now it's going to actually be based on h prime of k, where h prime of k is going to be the size of the hop. That'll be how big of a hop the bunny can take with the rocket-powered boots. So here's the idea. So remember, this should remind you a lot of the linear probing. So instead of it being where it's just h of k plus 1 mod m. Now it's h of k plus h prime of k mod m. And then I have it where I go up to 2 times this, 3 times this, and we'll go 4 times this, 5 times this, until we find the appropriate spot. So everything we talked about last day about linear probing is the exact same idea here for double hashing, except now the probing sequence is different. Everything else remains the same though. So everything we talked about where we do the hops and everything, the only thing that we've changed is how these hops occur. So instead of it being by 1, now it's going to depend on the secondary hash function. Everything else we talked about, the algorithms and everything will be the exact same other than this. Is that clear, everybody? So we're going to be trying to resolve this issue with the clustering by trying to make it so that the hops are a lot more dependent on the key's value, and they're going to vary. They're not just going to be 1 anymore. So I want to make some few remarks about h prime of k for us. So the first thing is because h prime of k is, you think of this as the hop of our rocket-powered boots for our bunny. We got to think about it as a hop size. So how big is the hop? So we cannot have this function spit out 0 as output ever. Otherwise, we will have a problem, right? Can somebody tell me why that's a problem? Why is that a problem? It go back to the same slot over and over again. Exactly, exactly. So our bunny is just, instead of hopping to another slot, it'll just be, okay, I'm just going to kind of it's just going to be hopping like this. It'll just be, it'll just hop in the same spot over and over and over again. So that's why we need to make sure that it never outputs 0. Because it dictates the size of the hop. So here's a useful and effective secondary hash function. It's a very common one, and it uses prime numbers, in particular the way it's formulated. So this one uses an approach where you design it where you're going to have it where you have the key coming in as input, and then you're going to have a prime number called q. So q is going to always be less than the table size, just to be very clear. So this is going to be a prime number. It's going to be less than the table size, and it's going to be q minus k mod q. So this is the proposed secondary hash function that we're going to use. It's a fairly effective one. And the thing you might ask, okay, so why this one? You're going to see in a moment that by using this, we can ensure, if we make sure that the table size is a prime number, we can ensure that we can actually visit every slot in the table. So the big thing you want to know is that q, it must be a prime number, and it must be for this secondary hash function that capital M, the table size, must be a prime number. For this to work, just always is guaranteed to work. So because remember, q, you have choice of q. Like if you want to make, for example, if the table size is say 15, you can make q, for example, you can make it say 3, you can make it 7, for example, you can make it 11. In fact, you can see that if you take this very carefully, you can actually get back linear probing. But I'll let you think about that. So what I want to do is I want to do an example showing you how we can do this. And I'll have in the notes a modification of the put algorithm showing you how we would modify the sequence where we use the probing sequence. It's really just one line in that algorithm. So if you took a look at that pseudocode, you'll find it's like the exact same, except I just changed one line in it. So let's talk about this. So first, is this clear, everybody? So all we're doing is changing the size of the hops. And we're going to use this secondary hash function to dictate the sizes of the hops. So I thought we would do an example, just so we could see how much of a difference it might make. Now remember, this doesn't guarantee we're not going to get any collisions. Collisions are still going to happen. So remember, that's why we're going to have this probing sequence. Because if we get a collision that happens, we need to go to the next position that's dictated by the probing sequence. So let's do this example. So I thought I would go through the same example we just did here, the one that had a clustering, the one we seen with the cluster. I thought we would just do it again, but we're going to do it with this double hashing. So let me just redraw out an empty table. Let's put some slots here. 1, 2, 3, 4, 5, 6, 7. So I'm just going to presume all of these are null initially. I'm going to have to use the same primary hash function. So k mod 7. So do take note that the size of the hash table is a prime number. Now the secondary hash function I'm going to use is going to look like this. So I'm going to use 5 for the prime number. So h prime of k is going to be 5 minus k mod 5. So remember, the whole idea is that I'm going to initially use the hash function. If that fails to happen, I'm going to go up by increments of h prime of k. So here we go. So I'm going to start off with h of 1. So I'm going to go through the same sequence. So I'm going to start off with 1. Well, we know that's just 1, right? So I'm just going to put 1 right there. There's no issues at all. Next, let's go with 8. So h of 8 is 1, right? Okay, well, that's a problem, right? We have a collision right here. There's a collision. So what do we have to do then? So remember, we're not going immediately to the next spot guaranteed, right? We're going to use the secondary hash function, right? So let's compute out what h prime of 8 is so we can find out how big the hop is going to be. H prime of 8, well, what is that? So it's 5 minus 8 mod 5. Well, 8 mod 5, well, let's think of it. How many increments of 5 can you take away from 8? Well, you can take 1 5 away from 8. That leaves you 3. So yeah, exactly. See, the chat's well on this. I really like this. So that means we have 5 minus 3. So h prime of 8 is 5 minus 3, which is equal to 2. So that means that we're going to have hops of size 2. So it means that when I get a collision here, I'm going to take this position, I'm going to add 2 to it to try the next one. If there's a collision there, I'm going to add 2 again. And if there's a collision there, I'm going to add 2 again. So the bunny is going to take, it's going to hop over from 1, instead of it just being 1, it's now 2. So let's try this out. So now, it means I'm going to go from 1, because there's a collision, I'm going to hop over here. I'm going to put 8 in here, as opposed to in 2 before. So now 8's right there. So far, are we doing okay? Are we doing okay, everybody? So remember, when we have a collision happen, we're going to appeal to the probing sequence until we find the next available spot. Okay. So it seems like give me 2 thumbs up if we're doing okay here so far. Okay, great. So let's do into the next one. So we got h of 3. Uh-oh, we got a collision here. So notice that we have a collision right here. So I'm going to apply the secondary hash function. Well, h prime of 3, well, the great thing about this is it should look really funny to you because we just kind of computed this already, sort of. So it's 5 minus 3 mod 5. Well, 3 mod 5 is 3, right? So that means that h prime of 3 is just 2. So I'm just going to take a hop size of 2. So I got a collision here, so I'm going to hop by 2 here. So then I get 3 right here on slot number 5. Okay. So now we got the last one, 29. Well, we established that h of 29 is 1. Well, we have a collision right here, right? So we're going to need to perform some sort of hop. So we need to figure out how big the hop is. Well, let's see what happens. So we got 5 minus 29 mod 5. Well, think of this. How many 5s can go into 29? Well, 5 of them, right? Because 5 times 5 is 25. So I take 29 minus 25, I end up with 4. So notice I have 5 minus 4, which is equal to 1. So the hop is going to have size 1. So it's just going to be just like our example with linear probing. But now notice that I'm just going to hop immediately right here. I'm just going to place that right here. But notice that now we don't have the clustering happening because we're spreading them out more because their hop sizes are now variable. Does everybody see that? So is there any questions about my example here so far? So just while you're thinking of anything, I just want to remind you that get, put, and remove are all going to function the exact same, just that we change the probing sequence. Are the same as before, except with the new probing sequence. Everything else is exactly the same. So if you aren't convinced by this fact, I have in the notes the pseudocode for put. You'll see that it's nearly identical. It's just really just one line changes. Instead of it being where you hop by 1, it's you hop by h prime of k. So it means that if you actually look at the worst case time complexity, that means that it's going to have the exact same worst case time complexity again. You could think of the situation where the table is pretty much full and you have to hop around through the entire table. So that means that you're still going to have for all of these operations, it's still going to be that you still end up with the exact same complexities, but I want to stress one thing. Remember, we still added in one new thing, right? So I got to make sure I take that into account. Remember, computing the secondary hash function takes big O of 1 worst case time, right? So that's another thing that we need to take into account when we say this, is that the worst case and the average case are still the same, but this is also because when I do this, I'm doing this because the secondary hash function still takes big O of 1. That means that if ever I need to go to the next position in our probing sequence, it's still, each one takes constant time to compute. So the worst case and average case, same as linear probing. So remember, the whole idea here is that we're trying to improve on linear probing, at least performance-wise, but we're still not going to be able to resolve these complexity issues. We would need a little bit more mathematical machinery to make that happen. So I wanted to convince you of one other fact. Do you know I just said something just blatantly without convincing you of anything? Does anybody remember anything I said over here, like on the board when I had these notes here and I said, oh, it must be this certain way, otherwise it doesn't work? Does anybody remember what I was talking about there? Like I said something, and usually you know me, I don't get away with just saying things without telling you something about it. Yeah, the prime numbers, exactly. So you remember how I told you, oh yeah, look, the prime, there has to be like 2 prime numbers. Q has to be a prime number, and the table size has to be a prime number. I didn't say anything about that, so I want to illustrate why this has to be the case. Now, I must stress that proving a claim like this requires a bit more number theory to make it work, because it's based on modular arithmetic. So I'm hoping I'll give you a good intuition around why this has to be the case, for at least generally speaking. Now, of course, that doesn't rule out specially tailor-made constants that may not necessarily have this property, but most certainly this is a claim I'm making that is universal. So if you give me whatever Q is and whatever M is, if they're both prime numbers, this process will work. So I want to show you an example of how this can go wrong if we don't have these two in place. So I thought we'd do another example before I tease too much. So why must M be prime. So I'm going to try to motivate this with an example. By any means, this isn't like a formal proof or anything. It's just an example. So let's do an example here. I'm going to give you, let's try to put in 3 records here. So I'm going to use the table size of 8. So I'm going to have 8 slots. I'm going to have 8 slots. My 7's a little squished in there. So my hash function is going to be h of k is k mod 8. My secondary hash function is going to be h prime of k, which is going to be 7 minus k mod 7. So I've chosen 7 as the prime number. Then I'm going, now notice that the table size, however, is not prime. It's 8. 8 is not a prime number. It's a composite number. So for example, some factors of this number include 1, 2, 4, and itself 8. So let's go through some records here. So the ones I'm gonna put in here are 2, 6, and 10. So let's start off with 2. So h of 2, well, naturally this is just 2, right? It's less than 8, so you know it's just gonna be a 2. I put that right here. Okay, let's go with 6. Okay, 6, easy enough. It goes right in. Because it's less than 8, you know it's going to just be a 6. Okay, let's try putting in 10 now. So let's put in 10. Well, h of 10, well, remember that's 10 mod 8. Well, 8 mod 8 is 0, right? That means 9 mod 8 is 1. That means 10 mod 8 is 2. Well, look. I'm going to get right here, so I'm going to get a collision that happens. So I go to my secondary hash function. I'm going to compute h prime of 10 just to see how big our hop size will be. So I'm going to have 7 minus 10 mod 7. 10 mod 7 is just 3, right? Because I could take 1 7 into 10, and I subtract that off for the remainder, which would just be 3. So I have 3 here. So 7 minus 3 is just going to be equal to 4. So the size of my hops for my probing sequence are going to be 4. So watch this. We'll just watch this. Now, I encourage you to walk through the process of applying the probing sequence, but I'm just going to do it just on hand here. Okay. So watch this. So imagine my bunny with the rocket boots. I get a collision right here, so I'm going to add 4 to this. So I'm going to go 1, 2, 3, 4. That gets me right there. There's a collision right there. So remember, I'm going to apply another multiple of the hop size. So it means that it's just going to be another 4. I'm going to add 4 again. Well, let's see. Remember, it's mod m, so it's going to wrap around. So we got 1, 2, 3, 4. So if I do this again, and I do it again, I could do this. Is the bunny going to eventually find a spot to put themselves into? Question: is this bunny ever going to need to stop with the rocket boots, or is this bunny just going to be? I don't know. I don't want to describe it. Just the bunny's going to get very tired. Is the bunny ever going to find a spot for 10? Well, think of it. Every time it's going to keep going up by hop sizes of 4. But here's the thing. Because of the divisibility of these numbers, based on 4 and the 8 being the way they are in this table, because of the multiplicity of these things, what happens is when I give you a position like 2, and I can keep going up by multiples of 4, I've set this up specifically so that I'll have something sitting right here as a multiple of 4, so that when I come back around, I'll be back to where I started. So this actually will cause this to happen forever. So there is not going to be a spot for the bunny to put 10 in. So this is going to be a problem. So 10 never gets inserted. That's a problem, right? So if we tried using our algorithm for put, in this circumstance, it would have some problems quite quickly. In fact, it wouldn't find a spot. That's a problem. So obviously we put some safeguards in if this ever happened. You just simply keep your counter going up by until we reach about M, and then you'd say, okay, I can't insert it. But obviously you would never want that to happen. You'd want to actually insert it because there's obviously a lot of free spots here. So you might ask, okay, so why is this happening? Now, because this isn't a number theory course, I would otherwise tell you a little bit more about this, but I want to tell you about a couple of concepts here that you might find a little bit interesting. So if I give you two integers, are called relatively prime. Relatively prime. Some people call this coprime. Coprime. If the only positive integer factors, or divisors, if you prefer to use that term, positive integer factors that divide both numbers. Both numbers is 1. So for example, if I give you 3 and 8, say, for example, 3 and 8 are relatively prime. Why? Can somebody tell me what the integer factors or divisors of 3 are? Could somebody tell me? What are they for 3? We already talked about 8, actually. What about 3? Well, think of it. Yep, it's just 1 and 3 because it's a prime number, right? It's a prime number. So if I have 3 and 1 are the divisors for 3, and the divisors for 8 are, let's see, we got 8, 4, 2, and 1. Notice that the only two they have in common with each other, so if I look in this bucket and look in this bucket, the only one they have in common is 1. So that's the only one they have in common. We can say that those two integers are relatively prime. Now here's the thing. If I give you a secondary hash function that looks like that, if I give you a prime number against any other number other than itself. Now remember, Q has to be, the Q, that other prime number that's used in the secondary hash function, is always less than M. So if I give you M as a prime number, and I test that against any one number that gets spit out of the secondary hash function, which may not necessarily be a prime number, is it relatively prime? So think about it. So just like my example here, notice that 3 is a prime number, 8 isn't. But notice they're relatively prime because if I give you a prime number, notice that the only factor they have in common, because that's a prime number, that's not necessarily a prime number. But notice that the factors I have them set out like, just in this specific example, notice the only common factor is 1. But here's the thing. If I make sure that this prime number is always bigger than any one number I can compare it against, I know that it will not have any common factors with any other number if I give you, say, the secondary hash function step size versus the table size. Because the table size, if it's a prime number, it's always going to be that its only common factor is always going to be a 1. So that's actually that's my hand-wavy way of me explaining to you how this will guarantee something number theoretically speaking, that we can guarantee we can always visit every one of the positions in the table. So to prove this claim, it takes a little bit more number theory, so we're going to kind of skip over that right now, but I hope this intuition is helpful for this. So the big thing that I really want you to know about this is that M And any output that comes out of the secondary hash function must be relatively prime. And if you have this, then you can visit all of the slots in the table with your probing sequence. So I'm not going to prove this here formally for you, but the thing is, we can always guarantee you, if we have this set up, that we can visit every one of the slots in the table using our probing sequence. Is that clear, everybody? So just keep in mind, with double hashing, the table size must be a prime number. So are there any questions about this? Is this kind of interesting? So you don't think that this might come up. It comes up every once in a while, especially if you think about hashing. So I want to make a couple of remarks about the load factor again, and before we move on to our next topic. So let's talk a little bit. I want to talk a little bit more about the load factor, okay, everybody? So I want to come back to the load factor a little bit, just to give you some insight into how these different these collision resolution schemes play out. So the big thing I want you to know is that the different hashing policies, these collision resolution policies, what they do is they actually guarantee average numbers of collisions differently. So it is the case that each one of these has their own benefits for different load factors. And you'll see is like the obvious winner out of the three I've shown you, but I'll plot it out for you. So I'm just going to call this revisiting the load factor. So I'm going to include a little bit more details about how I've plotted these in the notes, but I will not ask you to remember the functions that represent the average number of key comparisons. Revisiting the load factor. So I'm just going to plot it out. You know how I am with this stuff. So I'm going to draw a beautiful chart showing you, so if I have the load factor being 0, 0.5, and 1, so this is the load factor over here, and this is the time. So if we're talking about the average number of key comparisons for the get operation. For get by collision resolution. So I'm going to plot this out for you. So remember, this is still the average number. So if you want the function specifically used for plotting this, they're going to be in the notes, because you don't need to know these specific details here, because I'm not formally proving them for you. We only talked about one of them, and I gave you intuition for it. But I thought I'd give you an idea of how this is. So separate chaining, the good news is that separate chaining is actually quite good. So separate chaining will look linear like this. So it's a little bit more shallow than just this. But this is what separate chaining will look like, comparison to the others. Is by all means is the superior one. But remember, its drawback is that we use more memory. But what happens next is that when we get about a little over halfway, they sort of diverge like this. Double hashing will start behaving much more like this. And actually, sorry, this should be lined up just with this. Let me just straighten that out. My apologies. You knew you were going to get this. So they're all going to be roughly in line with each other for small load factors, which makes sense given the fact that the table's mostly empty, right? It's just when you start getting to around halfway full, things start really diverging. So linear probing, however, is like this. So if I were to plot out the average number of key comparisons, it'll look something like this. So if I were looking and measuring this out, what would you say for general alpha? Which one of the three is the best one? So far I got one for separate chaining. Yeah, it should be quite clear from this chart that separate chaining is the best of these three. The main reason why is every time we have a collision, we just simply use more memory, as opposed to the intuition I can help you have here is that, you know, when we do collisions and all that stuff with our open addressing, we're using parts of the table, right? That's one explanation for this, is that when we actually do this process, we're using the table directly in our open addressing. In separate chaining, we actually just use more memory, so we're not occupying additional slots. So that's one reason, among some others, that I won't get into here. So if you're thinking about which ones are so I'm going to rank them for you. For general alpha, you got linear probing. So you got linear probing is like your worst of these three. Then you have double hashing. And then you have separate chaining. And I'll put in quotation marks, out of the three, this is the best one. And this is the worst one. I'm not claiming these are the best and worst universally. I'm just saying out of the three we studied, this is the ranking of them. That linear probing performs the worst, separate chaining performs the best. But keep in mind, remember thinking about trade-offs here. Notice that the double hashing is about comparable with separate chaining when the table is about half full. So something around 0.5 or 0.6, you might consider with double hashing, maybe when you start exceeding past this might be a good time to rehash the table, resizing it. So what you might say, Dan, why are you showing this chart? It gives you an intuition for when you might need to rehash the table. So like I said, if you're doing double hashing, I'm just going to abbreviate that as DH. Notice that around 0.5 or 0.6, this is it's pretty comparable with separate chaining. So around 0.5 or 0.6, these are about pretty comparable. But if it gets bigger than this, then you might consider rehashing, if you want to take advantage of the same kind of performance that you might get from separate chaining. You notice that linear probing, it's much, much less. It's like something like 0.35, 0.45, right? So the intuition here is I'm giving you some ideas for when you might rehash the table to match performance of separate chaining. But the big idea here is that those two don't use additional memory. They just use, well, technically we always use additional memory in hashing, but it most certainly is not going to go erratic on us. It's always going to be, we have control over the table size. So are there any questions about this? So I thought I would mention this for you. So this should give you some intuition about performance-wise, how you might consider designing your hash table. So keep in mind the few things. So remember, when we talk about separate chaining, the big thing is maintaining that load factor is something like a constant. Then you can guarantee on average it's going to be big O of 1. Other thing is, keep in mind things like, is it more than halfway full? So is there a situation where linear probing is the best? That's a very wonderful question. Off the top of my head, I'm not sure. But most certainly you can see that very early on, when the table is mostly empty, you'll notice that these three are not much different. So if you have a pretty big pretty big hash table, you could just simply get away with linear probing if you're not going to put a lot of records into it. So that's one intuition you could get from this right away. I must note that technically this is a little bit steeper, but it's slightly steeper than that. But you'll see that for different load factors, you can get something that's roughly comparable to separate chaining. But if you keep it a little bit under a half full with linear probing, you're pretty much fine. It's just that when it starts getting really full, then you're going to start getting those phenomena we talked about, ranging from if you start getting clustering occurring, that's one issue. Another thing, of course, is the issue of if you plan to do deletions. That's another thing you have to keep in mind. If you plan to use your hash table for deleting, if you have a remove operation you're using, that also can impact linear probing and double hashing as opposed to separate chaining. You're actually just doing deletions in a linked list, right? So these are all things that you might consider in practice. So I'm trying to give you some motivation behind both sides of this. So a couple of things I want to mention is that this is by far not the end of hashing. You can take entire courses about this topic. In fact, it sometimes makes entire sections of courses like in crypto. cryptography, for example. So there's other topics out there beyond this course that I just want to mention to you, because I just think that they're interesting, but they're beyond the scope of this course. For example, so remember that hashing is a fairly mature topic. Like, it has been studied for decades at this point. So there's a lot we know about hashing, but there's other things that are still actively being researched. So there do exist. So first thing I do want to mention to you is that there do exist hashing functions. So there do exist hashing functions that allow 0 collisions. So they do exist, meaning that they do not require collision resolutions at all. It just requires a lot more setup for them. This is something that we will not talk about these, but they are called perfect hash functions. You can guess why they call it a perfect hash function. So there's a lot of juicy mayonnaise and mustard around this topic. So there's usually these families of functions, and they fall under what we call perfect hash functions. Another thing is, you know, when we talked about, like, when we do get and all these operations, we had our average case was big O of 1, right? Constant time. Now, there do exist different hashing approaches that actually can guarantee constant time in the worst case for certain operations. So I also want to say that there are types of hashing that support big O of 1 worst case get operations. So if you want to do get in truly big O of 1 time, these do actually exist as well. They are not nearly as complex as perfect hash functions, and they usually use some of the techniques that I showed you here. So for example, it may use like a secondary hash function. One example of this is something called cuckoo hashing. It's called cuckoo hashing. You might guess what that's about. So how many of you have ever heard of the cuckoo bird before? So I'm talking about an actual bird. So it's called the cuckoo. Okay. So there's these cuckoo birds. So the reason why it's called cuckoo hashing is the idea is that, like the cuckoo bird does, so a little bit of the story behind this is the cuckoo bird will knock eggs of other birds, so they will take over the nests of other birds and knock out the eggs so they can put their eggs in. So they go through this process of basically co-opting other nests, and it knocks out the eggs of the other bird. And so that the other bird takes care of their eggs, for example. That's one strategy you could use. So the idea of these hash tables is that you actually use a process like this. And the idea is that the secondary hash function is used for this knockout process. So it tells you where it should go. But yeah, so I thought I would just mention these couple of things for you. But are there any questions? But yeah, if you ever find yourself curious about these, I encourage you to look into them. Cuckoo hashing is surprisingly simple, but its theory underneath it is a little bit more complex, most certainly. That's also why I wouldn't talk about it here. Okay, so if we're doing okay, are there any other questions about hashing before we move on to our next topic? Because we're going to be moving into a brand new topic. It's going to feel very fresh from what we're currently doing. Okay, so if we're okay with this, we're going to move into a brand new topic. We're going to start talking about trees. So trees are going to play a pretty big role in the rest of this course. I would argue it's some of the most important stuff you're going to get out of this class. because a lot of data structures are based off of trees. Okay, so let's talk about trees. So new topic. So the first thing you need to know is that a tree is an abstract model of a hierarchical structure, so a hierarchy. So I'll give you an example here. So a tree is an abstract model of a hierarchical structure. That's my big fancy word for the day. Hierarchical structure. For those that aren't familiar with this word, it just simply means that you have it where you have organization based on ranks, for example, or it comes in layers. So I'll give you an example in a moment. So some examples, file systems. File systems are examples of hierarchical systems or structures. So you can organize, for example, a file system around the concept of a tree. Likewise, another example is the organization of a company. So for those that aren't really convinced that the file system is like a hierarchy, well, think of it this way. You make folders, you have directories, and they go downwards more specific, but they brought in at, for example, drives, right? But there's other ways you could formalize this, but most certainly that's a very easy way of seeing this. So you have folders, they can have subdirectories and so on. You can imagine them like they're being layered up from your most broadest class of where you could store files. So these actually can be represented internally as a tree. Yeah, family tree is another good example of a tree. I know that some people, say in the biological sciences, have all sorts of ways of representing these things too. There's so-called, I don't want to get too fancy or technical here. Some people call them laminar families. They also take the form of a tree. If you don't know what a laminar family is, don't worry. I'm just thinking about things off the side of my head. So if you're curious about that kind of stuff, like bioinformatics and stuff, they talk about some of these types of things. But yeah, family tree, most certainly that is a tree too. So just give me an example here. So I'm going to draw out an organization. I'm going to call it Compute. So the organization is going to be called Compute and Company. I know, a corny name for this company. So the overall structure of this thing is the name of the organization. Then there's different branches of this company. There's the sales part, the manufacturing part, and there also could be the research part. So these are different departments. You can think of as different departments. Likewise, their sales could be in Canada or they could be international. So there could be a Canada division of the sales department, and there could be an international division. In the manufacturing part, you can have people that work on laptops. You can have also people working on desktops, for example. Hopefully you're getting the idea. So, and of course, international, there could be some other places maybe they're focused in on. For example, they could be focused in on, I don't know, the USA. They could be interested in the United Kingdom, for example. Some other places too. Heck, they could be interested in Candyland. I don't know. That's a place that exists, right? It exists in my dreams. So this is just an example. So you could even have a tree like this that lays out the responsibilities or the roles of individuals in an organization too. Like you can have like the president or CEO. You can have different members at that rank. You can see it formulates a hierarchy. So a lot of these structures do exist. They manifest themselves all over the place. Heck, you can even think of just services, for example. You can think of, for example, flight companies have tier systems based on how much you use their service, for example. This is something that does exist. There's also memberships too, versus just typical guests. The idea is that these occur all over the place. So that's the big point I'm trying to get across to you. Now I got to give you some terminology for trees. So we're going to talk about some terminology. So this is how we're going to talk about trees. So I'm going to draw a tree over here, and we're going to start writing out some definitions. I know, you might say, Dan, definitions. Why are we doing this? Well, it's because we need to make sure we're talking in some consistent language here so that we know when I point at the do-ding versus the do-dah, we know exactly what we're talking about and we're not just thinking of do-dahs and do-dings. That's why we need to do this. Because otherwise, we're not talking in the same language and it gets very confusing what we're talking about. Then also, I want to make sure you're familiar with some common terminology when it comes to trees. Because it's used, this tree concept is used all over the place in data structures. So, I'm going to draw out a tree for you. I'm just going to label it with some letters. But I'm going to start off by pointing out that we're going to focus on specific kind of trees called rooted trees. You'll see why I call them that in a moment. Terminology. So a rooted tree is given below. So I'm just going to draw you a picture. So the big thing you need to know about what a rooted tree is there's a very specific node. So I'm going to use terminology that's similar to when we talked about linked lists. You know how we have nodes in a linked list? We're going to have nodes in a tree. Sometimes these are called vertices. Or if that's plural, or singular vertex. So we're going to have always in a rooted tree a special node that is dictated and called the root node. So there's always going to be a specially designated node called the root node. And similar to my picture over there, we're going to have it where we have potential, what we're going to call children of a node. B, C, and D. So each one of these, just to be clear, is a node or vertex. So usually in the context of data structures, normally they're called nodes. If they're used in the context of so-called graph theory, I'm not sure if you've ever heard of graph theory before. They're often called vertices or singular a vertex. Now, of course, like I said, just like a hierarchy will have, each one of these nodes has a parent-child relationship among all of the nodes. So, for example, this node has children. There's these 3 children. But likewise, all the nodes except for one, the root node, all have a parent. That's also a way you can know you're looking at the root in a rooted tree. So I must stress that all these lines I'm drawing, these are sometimes called edges, or an edge, or a link, or an arc, depending on context. I'll typically refer to them as edges or links. Usually edges. Now, I'm just going to draw out some more of this tree, just so we can kind of point at it and say, hey, look, it's that thing. E and F are going to be the children of B. Then we're going to have 3 more nodes that are going to be the children of F, I, J, and K. Now, I must stress that at this stage, we're just representing the tree. When you actually implement this, then we have to get a little bit more concrete about it, which I'll talk more about that either today or next class. So the first thing you need to know is that nodes have a parent-child relationship. So that's the first thing you need to know about trees. Can edges be considered pointers to nodes? That's where we're going with this, yes. Yes. So these edges are going to operate like pointers when we actually represent them. So you can think of these as nodes like you think of nodes in a linked list. We'll get more specific on how we represent this. But yeah, you can think of these edges as pointers, where you have it where each one of the links that gets you from a parent to a child can be a pointer from one node to another. And in some representations, you'll have it where there's actually a parent attribute where you point back at the parent. you'll see that in the way I'm going to be representing them with you, that'll be the case. But you don't necessarily need that for a general representation of a tree. So the first thing you should notice right away is that this is actually a generalization of a linked list if you actually look at it carefully. Can anybody see why I would say something like that based actually on the remark that was actually made in the chat? So think about it. Think about it. Imagine I have a tree where I imagine the root as the head. What would it look like then? So think of it, imagine you have a root node and you imagine the root is the head of a linked list. So right now we haven't gotten very specific, but I want to motivate why and where the ideas that we're going to be going with, where they might come from. So I like that somebody brought up that we can think of these edges like pointers. Well, think of it. If imagine I have a root, you imagine you just have all of the nodes like a big long chain. And you notice right away, boom, a tree is actually a generalization of a linked list. If you think of the linked list as nodes like this in this much more abstract way. Do you see that, everybody? It's kind of neat, but most certainly it's not necessary to understand this idea either. It's just that you'll see this when we actually implement the tree, how it might look. It might have some similarities with that. So I just thought I would bring that up. So let's talk about some more terminology here. So in this example, I would call A. So A is the root node. So we would call that the root or root node. Just to give you some clarity of how we would say these things, we'd say that B, if I look at node B here, it's the parent of two nodes, E and F. B is the parent of E and F. Now, you can also have this idea of siblings. I like that somebody brought up family trees. So you can look at this almost like that. In fact, a lot of this terminology is very natural to think about in terms of family trees. So if I think of one node that has a common parent with another node, we'll call that a sibling. So for example, C is a sibling of B and D because they have the same parent, right? Now, like I said, nodes have parent-to-child relationships. So B, C, and D are children of A. Now, we're also going to have some other ideas like descendants and ancestors. So if I look at node B here, if I want to know all my descendants, it's not just the children, but it could potentially be their children and their children and their children and so on. This is what we're going to refer to as the descendants of a given node. So in this case, E, F, I, J, and K are descendants of B. So note that if ever I give you A, like if I look at A and I look at its descendants, every one of the nodes must be a descendant of A except for A, of course, right? So likewise, you can also define the notion of an ancestor. So for example, if I look at J here, let's find J here. The ancestors of J would be the parent, the grandparent, the great-grandparent, and so on. So if I look at J, J's ancestors are A, B, and F. Can somebody tell me which node is the only one that has no ancestors? Which node has no ancestors? It's A, right? The root. The root always never has ancestors. Very good, very good. So this is just some of the key terminology. I also have some other things I also want to define with you. So I'm going to write them all over here. So let me just make a note here, just right about there. We're going to write out some more terminology here, and we'll see how far along we get. If we can get this out of the way, then we can focus more on trees next day. Yeah, I think that might be a good place for us to stop today. So let's finish talking about some terminology here. So let's talk about an internal node. So an internal node is a node with at least one child. So can somebody list out to me all of the internal nodes of this tree? So it's a node with at least one child. So can somebody tell me what all of the internal nodes are? What are all of the internal nodes of this tree over here? So far we got A. We know A has at least one child. B has at least one child. C has at least one child. D does not, right? So we know that we have A, B, C. Let's see. We got some other suggestions. We got F, right? F has at least one child. I think that's all of them. Yeah, I think everybody's got it. Right on it, everybody. Good job. A, B, C, and F. Naturally, there's another notion called a leaf node. Sometimes these are called external nodes in some people's terminology. So if you ever hear the term external node, it's the equivalent of me saying a leaf node. This is in contrast to internal node. So this is just simply a node with no children. Naturally, these would just be all of the nodes we did not list here. So there's other terminology I want you to be aware of. Depth or level of a node. So there's depth or level of a node. This is just simply the number of ancestors it has. So for example, if I give you node E, what's the depth of node E? What's the depth of node E? Yeah, it's just 2, right? Because it has 2 ancestors. Okay, how about the height? Now the height of a tree. So a tree's height is just simply the maximum depth of any one node. It's the max depth of a node. So can somebody tell me what the height of this tree is? What's the height of this tree? It's 3. Very good. Very good. Notice that if I start all the way down here and I count how many ancestors I have 1, 2, 3. Another way you can also define it is the maximum number of links from a leaf node to a root. So for example, notice how many edges I would need to get there. It's 3. So in our example, this would be 3. Now, there's 3 other terms here. I'm just going to give you the last one here. Well, the one that's going to be most interesting for us. The other 2 are the notion of an ordered tree versus an unordered tree. An ordered tree is simply one that imposes an ordering on the nodes. An unordered tree naturally does not. But a subtree, this is one that's going to be rather important for us. So it's a tree that consists of a node and its descendants. So for example, if I want the subtree of B, so this, for example, would be the subtree of B. And often I would refer to the root of this subtree as B. So just be aware that there's two different contexts. There's the designated root node, but there's also the idea that you can have a root of a subtree. So notice that this subtree is rooted, that's the terminology difference here, it's rooted at B. But anyways, when we come back, I'll give you how we can represent a tree like this, and then we'll start looking at what we can do with trees, okay everybody? So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.